Okay, so welcome back after the break. The next speaker is true fan of C++, a Boost library developer, principal software engineer at Sabre, the member of C++ Standards Committee, Andrzej Krzemieński. Let's warmly welcome him.
Thank you. Just out of curiosity, does anyone here know or use Boost libraries? So, one person. It's good for you. So, hi everyone. Thank you for attending this talk. My name is Andrzej Krzemieński. Yes, I'm a software developer. I work at Sabre Polska. There is a number of products and teams there. I want to share experience from one of them, which is called the IntelliSell. You might find it interesting because we have some heavy usage of C++ here. So the plan here is to talk you through what we do here in short, why we needed to migrate some of our applications to C++, and then, and this will be the core of this talk, to show you value semantics. This is the core and most characteristic feature of C++. So our application IntelliSell looks for cheapest or most attractive flight connections. You want to fly somewhere, you need to look for flights. You will probably use our application indirectly. If you use something like Skyscanner, you used our product. And the computational problem here is quite difficult. It's like solving a graph problem, finding all the possible flights across the globe, then finding all the possible fares, taxes. And the problem we are facing is if to compute the solution for you takes like 5 seconds, how can we return the response in 1/10 of this time, like half a second? And the answer to this question is we cache. So we cache not only the solutions that the previous customers sought, but we also cache proactively. We try to figure out ahead of time the most commonly used connections, markets, and just feed the data to the cache in the morning so that when you come, the answer is already waiting for you there. We just need to extract it from RAM. But for this to work, we need to store a lot of those solutions into RAM. And for this to work, we need to have those solutions be as small as possible. And this is where the choice of language comes into play. One example here, I will be comparing for a while C++ and Java. At some low level, we always store integers. So suppose integer is one word in memory. But in a big program, I need to use abstractions. So I will use a class like here that aggregates 2 integers. And we'll be talking in more abstract terms of points rather than integers. And now, if I want to compile this code and store this data, these points in memory, in C++, I get exactly what I need. Just 2 ints, they are just stored in memory. The programmer sees classes and thinks in terms of classes, but after the program is compiled, there are just 2 integers, nothing more. But if I wanted to create a similar class in Java class is something different. It's related to Java virtual machine. You may need to use a reflection, so some connection to this reflection mechanism has to be embedded in the object itself. Then you have a garbage collector in Java. It's a very sophisticated tool, and it needs to keep track of the state of garbage collection, and this state is also stored inside the object. So what I really get there is first I get this class pointer, which is all the description of the class that I may need for reflection, for instance. Then I have a mark word. Oh, did you actually hear me before? Because now I can hear myself. Sorry for that. Then we get a mark word, which stores all the other information that virtual machine may need. The state of garbage collection for this object, the mutexes, because in Java every object is lockable. You can synchronize on it, so the mutex has to be somewhere there. We need to store the cache if it has been computed, and only then do we get these two integers. So the signal to noise ratio, so to say, is 1 to 2. We've lost half of the space only because of the language overhead. That is, you may need it, of course, in different scenarios. It is very convenient to have a garbage collection and synchronization on every object, but in case you are interested in actually storing data in a compact way, you lose. I got that from studying the hotspot implementation of Java virtual machine. This is the one owned by Oracle now. It's open source. And I don't pretend to understand all this information, but I understand one thing. It's that hotspot Java is implemented in C++. And this is for a reason. If we go further with this analysis, if I want to aggregate 2 points in a rectangle, in C++, the layout in memory I get is 4 integers, x, y, for the 2 points. In Java, I get a class pointer, mark word, and then 2 pointers to 2 sub-objects. And for each sub-object, class pointer, mark word, x, y, and so on. Now the signal to noise ratio is like 1 to 4. So the loss is even bigger. And how do we store vectors in 2 languages? In C++, I get a, this is how usually data is, the arrays and dynamic arrays are stored in C++. I have a pointer and 2 sizes, the size of the allocated block and the size of the logical array. But conceptually, it's a pointer to an array somewhere. And then in this array, my points are laid out contiguously, x, y, in one block. In Java, if I wanted to store the vector of pointers, I pass it by pointer, because in Java you pass everything by pointer, to an array of pointers, and for each pointer it's a class word, mark word, and then x, y. And they are spread across different locations in memory. So again, the signal to noise ratio is like 1 to 2, plus the layout, the contiguous layout you get in C++ is CPU cache friendly. And this is important because in C++ we need to be aware of CPU caches. And this is because, again, we have to be aware that accessing data from RAM is a very expensive operation. Compared to the normal operations you do on a processor, adding, multiplying, it's relatively fast, but when you have to fetch data from RAM, it's orders of magnitude slower. The only other even slower operation is performing I/O. But RAM is sufficiently slow that you want to do too many clever things to overcome this latency. So usually what the hardware vendors do, they will provide some memory still inside the processor. So the processor is this size. The unit that really makes computations is very small, and the rest of the processor is just RAM. And we call it cache. So the data from the main RAM is copied and cached there. And if we are lucky, if we can find our data in cache, we don't have to do a round trip to memory, we save time. And the memory in this CPU cache is distributed through cache lines. Each cache line is like 64 bytes. And the way we fetch data from RAM is through these 64-byte lines. And of course, at some point, we have to get to memory, and we have to pay the cost. But the most common optimization that we can do is that if we need to do it, we would also take the memory that we will be used the moment after and the moment after, so that the next read doesn't have to go to RAM because it has been fetched in the previous read. I hope it makes sense. So this happens for arrays. If I iterate over an array, it's quite clear that if I inspect the nth element, I will inspect the n+1 element just a second later, and then n+2. So if they are laid out contiguously and they fit into one cache line, they will be fetched at one go. And I can inspect like 4 or 5 elements before I need to do the next read. But in order for this optimization to work, I need my data to be small and laid out contiguously. Only then do I have the guarantee that a number of useful pieces of data will be fetched in one go. But you will not hear us talk about CPU caches and cache lines every day. It's enough for us to say about keeping our data as small as possible and laid out contiguously. And this is what we actually care about in our day-to-day job. So how does this work in a program? This is a sentence that you would get from our business requirements, or generally from our business. We talk about flights. Flight is something like easy 58 something, goes from KRK to LGW and costs something in PLN. And what we see here is those, what we could call short codes. Airline codes, airport codes, currency codes, country codes, tax codes, whatever codes. There's lots of them in this industry. And if we were to represent them in a program, we might be tempted to use a string class from the standard library, because this is used for storing arbitrary sequences of characters. But we would never do it, because we know how std_string works behind the covers. Because it has to be prepared for storing arbitrary huge strings, the way it is implemented, it will allocate memory somewhere on the heap and will contain a pointer that will point to that memory, plus 2 sizes. In C++, it's usually like this. You have a pointer and 2 sizes, the logical size of the array and the size of the allocated storage, which are often different. But generally, it's this pointer and 2 sizes. And it will work, but allocating memory for if we want to store a 2-character shortcode is a huge waste of memory. And even the string implementations will not do it. Every decent string implementation will apply a clever optimization, and rather than allocating any memory, it will store the characters directly in the place of the pointer and 2 sizes, and just flag that it is applying this optimization, which is very clever because you don't have to allocate any memory, but it's still a huge loss, because you need, like, suppose we have 64-bit architecture, a pointer is 8 bytes, you have 3 of those, it's 24 bytes, whereas you actually needed 2 to store 2 characters, and in fact even less. So even that is not good enough. So what we'll do in that case is to provide our own type in form of a class, even though there is one ready for us in the standard library, but it's not good enough for performance reasons. So this is what we'll do. We'll create a code. It is a template because different codes have different sizes. Country codes are 2 letters, airport codes are 3 letters, and we'll just store an array inside. And of course, wrap it in a nice interface. And this way we guarantee that this class occupies only 2 bytes, 3 bytes, depending on this n. And in fact, because in C++ we care not only about performance, but also about safety, which we understand as bug avoidance, we would probably add another template parameter to this template only to control instantiations. And this way, when you need to operate with 2 3-letter country codes, like airport code and currency code. They are both 3 letters. They require identical storage, but they are conceptually different types. Because it's a second template parameter, we can instantiate with 2 different artificial classes, and they become 2 distinct types. You cannot ever confuse one with the other, because if you try, the compiler will give you an error. So this is more or less how our types are designed. And this is so much for the introduction. Now we'll go to the core of this talk, which is value semantics, the core underlying feature or characteristic feature of C++. There's just an interesting observation that the same notation, this x equals 7, means very different things in mathematics and in programming languages such as C, Java, C++, C#. In math, this notation means that whenever we refer to this name x, we mean value 7. Ever, always. Whereas in a program, this means that there is an object or a container or a box, something capable of storing a value, and at the given point in time, we are storing the bit pattern that corresponds to value 7. But it's at this point in time only, and at some other point in time, we can store a different value there. And this is where the intuition with mathematics breaks. But to some extent, we can maintain this illusion that we are using the mathematical notation. Like here is an example. I have a variable, call it object, equal to 1, b equal to 2, and then I select the max of the 2, which would be 2. Yes, I can print it, and it's intuitive, even to someone who has only who only understands mathematical notation, but not necessarily any program. But we know that inside the program, something different happens there. Like we have one object A, which contains value 1. We create another object B somewhere, which contains value 2. And then, this is not that obvious, we create a third object C, which happens to have the same value as object B. And the difference comes into the picture when we start to modify the values. When we modify the value B and set it to 0, the value of C doesn't change because B and C are separate entities. And this is actually the core feature, axiom, characteristic of value semantics. It's this value separation, which we could call or express like this here. If I have some original value of type T and I create a copy of it, however I try to modify the original value, it never affects the copy. The copy remains the same. So there is no way to change the copy by or through changing the original value. And this is the key observation, characteristic, and benefit here. In C++, the same thing applies to user-defined types. This is the same example as before, but now it's not int, it's the big int, some user-defined type. But the logic is the same. I create one big int A, then B, then another one C, which is the max of the 2. Again, I have 3 objects. B and C store the same value, but in different places. And when I modify the object B, this does not affect object C. And if you've programmed in C or C++ for a while, you find this quite obvious, but it is not that obvious to someone who comes from Java. Because in Java, the same code would mean something completely different. In Java, you pass user-defined types by pointers, which you call references, until you get a null pointer exception. But conceptually, there are pointers. They point to something. So the same code in Java means I create a pointer A that points to some object somewhere, which happens to store value 1, then make int, another make int, creates another object somewhere, but I only get a pointer B to that object. And when I call max, of the two, I create a third pointer. Well, it's just a pointer, and it points to the same object as B points to. And the effect is that if I try to modify the object through pointer or reference B, I also modify the object that would be referenced through pointer C. So suddenly I'm only touching B, but my C changes. This is where you can get caught by surprise if you migrate, for instance, from C++ to Java. In C++, we have the uniform value semantics for built-in types like integers and user-provided types. And with this value semantics in place, this is where it gets practically useful. You can return things by value. By default, when you just say you're returning point, it means you will be returning it by value. And this means the caller gets the guarantee that only the caller will be able to modify the value and no one else. So this is how it works. I have some shape, I can ask it for origin, and this origin returns by value. So when I get this point origin and I modify the shape by repositioning it or whatever, I have a guarantee that my point remains unchanged. Contrast this with the situation if the shape returned the origin by reference. If this happens, it means that the object is located somewhere else, probably inside this shape. If I reposition my shape, does the reference P change the value? Maybe yes, maybe no, I don't know. I cannot figure it out from this code alone because I don't know what's happening with this reference P because everyone else in the world can change it. I have no control over it. And imagine that this happens in a multi-threaded program where multiple threads can access the same object at random times. I just run potentially into many concurrency-related issues like data races. Then I need locking. Locking introduces other problems like deadlocks. And all this stuff is avoided if I just return by value, because then I have a guarantee that no one else will ever change my value. Another observation here and characteristic feature of this value semantics is that we may have many objects at play, but we are only interested in the value, and this value traverses from one object to another. Like here, I have this ans inside my function, then it's returned, another object always created in a different scope, but it's still the same value that traverses through those objects, and it's only this value that we are interested in. And we return by value also for efficiency reasons. Sometimes it's simple because this returned value may be smaller than the pointer we have to return. If we return by reference, we are actually returning by pointer. So the pointer may be bigger. But it's not this efficiency that I have in mind. The real problem, I can even return something bigger, like rectangle, composed of 4 integers. It may be bigger than the pointer. But because I'm returning by value, the contract here is that it is only the value that is of interest to anyone, not the object and where it is located. So we can see the rect written down here, but when the program is compiled, the compiler is allowed to just store the 4 integers into registers. Whereas when I return by reference, the contract here is that I need to create this object somewhere and then return a pointer to it, and then in order to get the value, I have to dereference the pointer and do a round trip to memory, to RAM. And when I do this round trip to RAM, I pay, because this is one of the most costly operations. Now, the value semantics in C++ are so much at the heart of the language that you get certain, I don't know, benefits or mechanisms here. If you have a value semantic type and you aggregate it into a bigger value semantic types, this property of value separation propagates. So if I have a point composed of integers, the same property I get by default. If I create a point C from some other points B or A, I know that my point C can never be changed through changing A or B. They are separate. And this value semantics property can even be applied to types that do not aggregate other types, like vectors. A vector is on the outside, in the interface, a collection of elements. But we know, and this is what we have to do, in C++, the implementation details are also part of the class contract. You have to know how the thing is implemented in order to be able to use it efficiently. So we know, and this is part of the contract, that inside a vector we'll find a pointer to a dynamically allocated array and 2 integers. So the array will be allocated separately. If you look into the class, it's just 3 little things. There's pointer and 2 sizes. If we wanted to copy that, we would get a disaster. We would have 2 objects pointing to the same array. This is how the memory issues arise. So we will not do it. Instead, when we need our vector to be able to create a copy, when we need a new value of vector, the author of the class, who understands all the mechanics, implementation, knows how to implement the cloning of this vector, which we call a copy constructor. So this copy constructor knows that it has to allocate a separate array with the same values inside, and then it will create a pointer and 2 sizes, and will have it point to the other array, and the 2 objects are now separate. You can even see it visually that there is no way to get to this new value from the old one. They are just distinct. And there is another way to do it, a more clever one, without having to allocate a new array. We could just create a new, this triple pointer and 2 sizes, and have the pointer point to the old array, and have the old pointer from the old vector point to nothing, assign a null pointer value. And this may look really scary, but it achieves the guarantee that after this operation, there is no way to modify the new value by messing with the old one, because they are still separated. It looks dangerous because the old one is now broken, but this is engineering, and sometimes we have to trade safety for efficiency. And third, there are situations where this operation is, this sneaky copy is really safe. Here is an example. I may have a function that takes a vector by value. Sometimes we take even vectors by value. I may add some points to this vector and then return it. And to return means that another object is initialized somewhere in the caller. This new object's value is produced based on the values I have here. But the interesting observation is that after this operation, this vector, which is called points, will never be read or used again. We know this is the last read, the last use of this vector. So it is safe to break it, to destroy its state, because no one will notice. And it cannot harm anyone. So this is where this sneaky copy, which we call a move, can be applied, and compiler really does it. In this code, there is no copying anywhere. This gets even more interesting when we consider classes that cannot ever be cloned, like fstream. It's something you can write to. It represents a file that you can write to or something similar. But the implementation of it is actually a pointer to a file descriptor that is maintained somewhere in the kernel. And there is no way you will be cloning those file descriptors. That would be a disaster. So there is no way to do a decent copy. It will not work. But we can still do this sneaky copy. Like we can have a new fstream point to the original file descriptor and have the old fstream point to nothing. And this is actually implemented, and it works. Like I can pass a fstream by value, write something to it, and then return it out. And again, because after the return no one will use it, I can steal the guts of this log, and it is safe and intuitive. And this is what the compiler does. You can return by value things that cannot ever be copied. And it goes even further. Because the value semantics is so prevalent in the language, the compiler is allowed in certain situations, like here when I have the object ans, which is a vector, potentially huge, allocates memory. I have it in a function, I return it. Then in the caller, I create another object vals, which will provide those values. The compiler is allowed to treat both of these ans and vals, as the one and single object, to the extent that if I try to read the address of one and another, practically on any compiler, I will get the same addresses, which may sound counterintuitive, but this is only when you think in terms of objects and addresses, which you shouldn't. The things we are taught sometimes at schools that there are stack frames associated with function calls. It doesn't work like this. The intuition here is it becomes intuitive when you think in terms of value semantics. Like the only thing that we are interested in is values contained in this vector. If you are only interested in this 1, 3, 5, which is in the vector, you will not be surprised. You are only surprised when you start thinking about the objects themselves. Like here, I was interested in the addresses, which is a property of the object, and this is where my intuition may break. But you normally don't do it in C++. It gets even further in the case where the object that I return doesn't have a name. Like here, I return a vector from a function, but there is no name for this vector. And this situation is special because when an object doesn't have a name, it means that I can read from it only once. And in this case, the compiler is required, as opposed to being allowed, to treat the object inside the function and outside the function as the one and the same object. And this means that I can return by value things that are not copyable or movable at all, like stud mutex. Mutex is something, a type where we are only interested in its address. This is the only thing that the mutex has, actually, in most implementations. And because of this guarantee that the compiler is allowed to treat the object inside and outside the function as the same object, we know that this is just one address that doesn't change. Now, another way of explaining value semantics is to show how you can accidentally break it. And this happens often when you use shared pointers. Like when you come from a language that uses garbage collector, it imprints some programming model on you where you can just allocate memory and have this garbage collector collect it for you when you don't need it. In C++, we are very aware of how we use resources, so we cannot afford to produce garbage, so we just don't produce it, and there's nothing to collect. But if you are in this under the influence of other languages, you might be tempted to think that shared pointer is like a mini garbage collector, but it isn't. And strange things happen when you try to think this way. So this is is a small illustration of the situation that actually often happens in practice. Like, I need to store something big, so instead I will be just storing a shared pointer. In this case, it's a book, and the state is the title. Normally, it would be something more than just the title, the contents of the book, or whatever. And now, in the constructor, I can just create this object, which is pointed to, and the pointer is stored in a shared pointer, and then if I need to read the title or set the title, I do it through this pointer. And it looks all fine. It seems to work to some extent. But if I try a more complicated use case, it starts to break. Like here, my original book is titled Mathematics. I make a copy, so the title of the copy is obviously Mathematics. Then I retitle the original to Physics, And all of a sudden, the title of the copy, which is const, which is supposed not to change, also changes title to physics. And how does this happen? Because we have the dangerous situation where two objects point to the same, read and write to the same memory. It doesn't matter that our copy is const, because the original has the mutating access to the same data. So what we've created here is something that Sean Parent would call an accidental data structure. And we broke the value semantics. All the intuition that the programmers have will now break. And you cannot easily see it from looking at those declarations. We can also pass arguments to functions by value. And this is different than passing arguments to functions by reference to const. And let's see how it works. This is one example at some point provided by Andrew Koenig, one of the fathers of C++. It's quite a common situation. We want to scale the values in a vector. So we pass the vector by reference, because this is the point. We want to modify somebody else's collection of data. And we provide a scalar by which it's called factor here, by which we will scale every element in this vector. But because it's a template, it's just this T, we don't know what this type is. It's potentially big, or rather expensive to copy. We would not pass it by value, we pass it by a reference also. A reference to const to be safe. And it looks convincing, but imagine this use case. I have some vector of values, like 4, 8 to 1 here. I find the maximum element of those, and then scale the vector by this maximum element. So it looks like the intention is that we want to preserve the ratios between the proportions between the elements, but we want to have them in the range from 0 to 1. It looks like it makes sense, but if we try to execute it, we get this result. First is 0.5, so yes, 4 by 8. Then we have 1, yes, it's 8 by 8. But then the following values remain unchanged. And in order to understand what happens here, we have to understand the difference between passing by value and passing by a reference to const. We may think that we are telling the compiler or the program to divide everything by value 8. But this is not the case. What really happens, we are passing a pointer. This factor is reference. So it's a pointer to some element of the array that is stored elsewhere. And worse still, we are passing another pointer to the same array through these reference values. And now we iterate over the array and modify its values. And at some point, we modify the object pointed to by this other pointer, this factor. And from now on, we are reading different value from this factor, even though this factor is a reference to const. This const doesn't change anything here, because the other reference isn't const. How you can fix it? You just pass the argument by value. And then the world changes, because now it's a separate value. Only you have the control over it. No one else can change it. So just to recap this, interesting, I think, observation is that when you pass by value, you get the guarantee that it is only you who can modify it and no one else. Whereas when you pass by a reference to const, you are guaranteed that only you cannot change this value, but everyone in the world can, including yourself, if you happen to get another reference to the same type. So in a way, those are opposite guarantees. But the downside is that if you pass by value, sometimes you have to make an expensive copy, which doesn't happen when you pass by reference. So we have, again, an engineering trade-off here between safety and performance. And the way we resolve it is by teaching programmers to actually pass by a reference to const and be aware that this situation will sooner or later hit you. And there is a, maybe you can see it already, tension between this value semantics and this object-oriented philosophy here. So far we've been showing a point which is just an aggregate of two integers. I could have provided an interface, the point interface, and then implement this interface with a class, add some virtual functions there, of course, to access the state of this pointer. But this changes the interfaces of all my functions. I cannot return just by value anymore. I have to return by reference to avoid any sort of slicing here. Because there's many implementations of different sizes. I don't even know the size of my particular implementation of the interface, so it have to be allocated somewhere else, and I can only pass a reference or a pointer or a smart pointer, but it's always through indirection, some form of a pointer. And this means that whereas if it was just a point with two integers, I would just point two words, probably in registers. I would just pass it like this. When it is a pointer to the interface, I am passing a pointer, and then this point points to an object. First element of this object is another pointer to virtual table. Then I have to do another dereference, and only then I have virtual functions that access back to the state of the object. So you can imagine how much it will cost, how many potential accesses to RAM. So we would try to avoid it unless this OO design is really needed. But of course, not every aspect of our program can be modeled in this way. There are things that are in natural way objects, like all the globals we have in our program, global state, global configuration. And in this case, the natural way of thinking of it is like an object that changes state over time, and we're interested in these changes to observe these changes of state. The system itself, the system functions, is like one global object. Its state changes over time, and we are interested in all those changes. As the new files appear in the file system, we want to know it. I/O is another thing like that, where the object intuition is more natural. So this is not to say that value semantics is another panacea for every possible programming problem. It's just to encourage to see how many parts of our programs can be modeled in terms of value semantics. Because each part of the program modeled this way makes the code easier to optimize, easier to understand and think of, and easier to get correct. And note that in the examples, I use this notation, this max of A and B, like in mathematics. I never use the notation like A dot max B, because for one, it doesn't look symmetric. And second, there doesn't seem to be any point here. I can have thousands of functions that operate on two integers, A and B, and it wouldn't make sense to make those 1,000 functions member functions of something. Also, I didn't use this notation because I don't need any object only for the purpose of this max being a member function of something. I don't have to do it. I can just call it max. And God forbid, I didn't use an example like this, where I have some factory that makes some abstract selector and then calls another virtual function select. And all the memory access things aside, it's just for clarity. If I need to debug some program because I know it has a bug, and I encounter code like this, and now I have to go through different files to see what this selector factory does, and then what this select function does and what it calls, only to find that it computes a max of two values. That would be a huge waste of time. You may find yourself in a situation when you are writing the code like this, and you sense that something is wrong, but you're afraid to say it because all your colleagues write code like this. Half of the internet tells you that this is how you should code. Even the books written by successful people tell you that this is how you write code. This doesn't necessarily have to be the case. Another answer may be that even if the half of the world codes like this, maybe they are not right, maybe they are just following the mainstream. So this is what I learned in my IntelliSell team. Now the commercial part here. Because when I joined IntelliSell, I observed that people here provide solutions, write solutions that fix their problems and not necessarily follow any mainstream. And we work on, this is what I usually tell people in the interviews, we can work on GCC 9.2, which is relatively new, and it's more or less C++ 17. We also compile with Clang just to get better diagnostics. We use Clang Static Analyzer, for instance, to detect more bugs statically. We use Boost libraries. I myself am a Boost library developer. We use our internal homemade tasks library. We have an entire framework for performing asynchronous computations, which is a piece of art, actually. Some people love it, some people hate it, but it always imprints something on you. We support a lot of developer initiatives, which you usually find important. So if we had a situation when someone comes and says, this unit test framework is obsolete and I would rather have a new one like GTest. So the guy was given time to actually rewrite all our tests. We have this weekly C++ chats, which originated from our IntelliSell team, where you can learn things you normally don't learn at schools or in the internet. Like we had a sequence of sessions now on Boost Ratio, this asynchronous input-output library, and how it works with C++20 coroutines. And we are represented in ISO C++ standards committee, so we not only use C++, but also help make it. And two of our Sabre representatives are from the IntelliSell team. So I think that's it. Thank you for listening to the end. And if there is any questions or comments you might have, I'll be happy to hear them.
Yeah, any questions? Oh, great.
Hi, I want to ask you about the slide where you introduced make values function, that one which created a vector and returned it immediately. You said about the feature of, yes, that one. It was, I'm not sure. Make values function.
Make values, okay.
Yes, that one. So you said that we can avoid copying or even moving the object. Is it so-called copy elision optimization, or it is something completely different? Because I remember this as a so-called copy elision.
Yes, this is called copy elision, or sometimes it's called named return value optimization.
Okay.
That would be it.
Thank you. And one more question. How is it implemented? Is it like that the function can refer directly to the stack frame on the upper level, Okay, so
Yes, like
it-
as if you passed a pointer to
okay,
this.
okay, that's all. Thank you.
Okay, and the next question. Yes, so I would like to ask about C++. So basically, it's becoming less popular language apparently. For example, introductory course to programming at universities are now in Python, not in C++. And what do you think is the future of C++?
I think it has a stable future in its domain. Like you will not use C++ for writing things with interfaces, but for microcontrollers or for implementing Java just-in-time compiler. You don't have any other alternative. Maybe you have something like Rust now, but it's relatively new. When something has to be really fast and doesn't necessarily have to have any interface, this is where C++ is the only option. And it's true, it's not really taught in universities that much. Probably one reason for that is that it is difficult to learn. It's a huge language, and it takes like 3 years to really feel comfortable with it. So maybe it's not a good starting point. But it's also a good way to secure your job. Once you learn it, you know you will be needed at some point.
Okay, thank you for the lecture. So massive thanks for Andrzej. This lecture is brought to you thanks to our gold sponsor, Sabre. Feel free to visit their stand. Feel free to take part in our contest. So around the building there are many QR codes. Scan them and take part in our contest. And the next lecture is about blockchain, cryptography, and NFT. See you after the break.
Thank you.